Direct comparison test. Before we look at the formal direct comparison test, I want to help build your intuition about when it's going to be helpful to us. So I want you to try to follow along with this visual example that explains the concept behind it. In this example, this is you. And pretend that you're standing maybe about a mile away from a door that you want to walk through. But this isn't a standard size door. And from where you're standing, you can't determine whether or not you'll be able to fit easily through this door. Well, it turns out that your friend is already down there. So here's your friend, and you know that your friend is taller than you, and they give you a call and they tell you, hey, I fit easily through the door. Would that be helpful to you? Yes, it would. If your friend, who you know is taller than you, definitely fits through the door, then you, who are shorter, should make that walk all the way down there. It'll be worth your time. You will also fit through the door. So basically, was this helpful? Yes, because your friend was bigger and your friend fit through the door. So that gave you information that was helpful. You, who are smaller, will also fit through the door. Here we have another similar example. Same situation, here you are, here's a door that's really far away, and from where you're standing, you can't tell whether or not you would fit through that door. But once again, you have a friend who's standing right in front of it. So there's your friend who's standing right in front of the door, and you know that that friend is shorter than you are. And that friend is down there, and he takes his phone out and gives you a call and says, nope, I don't fit through the door. Is it worth it for you to make that trek all the way down there? No. If your friend is shorter than you and they don't fit through the door, then there's no way that you are going to fit through the door. So was this a helpful piece of information? Yes. So here, your friend was smaller and doesn't fit. So that was a helpful case. With that in mind, now let's take a look at the formal direct comparison test, often abbreviated DCT. Suppose A sub n and B sub n have non-negative terms, so basically positive or zero terms, and capital N is some integer. If A sub n is less than or equal to B sub n for all n greater than or equal to capital N, so what this really means is eventually. So this phrase translates to eventually because when we talk about infinite series, we really care about what's happening at the tail of the series. So as long as eventually a sub n is less than or equal to b sub n, and if the sum of b sub n converges. So I'm going to pause right there. B sub n is greater than or equal to a sub n. So if b sub n, if the bigger series converges, then the sum of a sub n also converges. This is like that first example where your friend being taller or bigger fits through the door. So if the bigger series converges, then the smaller one must converge. You, who are shorter, must also fit through the door, must also converge. For the second part, we have if b sub n is less than or equal to a sub n, eventually, for all n past a certain point, and if the sum of b sub n diverges. So remember this time, b sub n is less than or equal to a sub n. b sub n is smaller. So if the smaller one diverges, or doesn't fit through the door, then the sum of a sub n also diverges. So if the smaller one doesn't add to a finite number, then a collection of numbers that are bigger is also not going to converge to a finite number. So it's also going to diverge. So this is the formal direct comparison test, and these are the cases that are helpful. So a bigger series that converges is a helpful comparison, or a smaller series that diverges is a helpful comparison. And so try to keep that analogy in your head about the whole going through the door thing, because not every comparison is helpful. Let's try to take a moment to understand when a comparison might be helpful and then not helpful. So here I have this list of numbers b sub n, and let's say we know the sum of adding up all of those numbers does converge. Well, if I happen to have a list of numbers that is always smaller, so underneath this particular list of numbers, let's call that a sub n. Well, because it's smaller, it's underneath, yeah, adding all of those up would also converge. So that is the helpful direction. So we had a bigger one that converges. We know that the smaller one must also converge. So now let's say we have b sub n again, and b sub n converges, and then we have a sub n happens to be bigger than that. Well, the sum of a sub n, that could still converge, but it could also diverge. So if I'm bigger than something that converges, I mean, I could still converge technically, but because I'm bigger, that could be too big and could go to infinity and could diverge. So that is a not helpful direction. So to help, again, kind of keep it straight, I like to go back and reference kind of that door analogy, or just really focus on the fact that a bigger convergent series is helpful, or a smaller divergent series is helpful. So BC, SD. Because we're going to have to think about what function's bigger than what, here is a hierarchy of functions that can help us determine those comparisons. So the fastest growing function is going to be n to the n. That's even bigger than n factorial. Then we have exponentials with bigger bases, so 3 to the n would be bigger than 2 to the n. And those are all bigger than polynomials, so something like n squared. And n squared is bigger than n to the 1.1 because 2 is bigger than that exponent 1.1, which is bigger than just n to the 1. The square root of n is, of course, n to the 1/2, that's smaller. The cube root, that's 1/3 exponent, that's smaller. And the smallest types of functions are logarithms. And so this is our hierarchy of functions. Now, we deal with a lot of quotients. And so here, if I take the reciprocal of all of these, then notice that the inequalities flip. So 1 over n to the n is now the smallest, and then 1 over natural log n is now the biggest because we are taking the reciprocal of this hierarchy. Let's jump into some examples. Does the sum of n equals 1 to infinity of 3 to the n over 2 plus 5 to the n converge or diverge? So to use the direct and limit comparison test, we need all positive term series. So just something to keep in mind. And yes, this is all positive terms. And so now what we want to do is attempt to create an inequality. Then we want to know if that inequality is helpful. So here, what are we going to try to compare to? Well, the easiest types of functions to compare to are going to be either geometric or p-series, because we can tell just by looking at them when geometric or p-series converge or diverge. So here, what we want to compare this to is 3 to the n over 5 to the n. So we can see that it's just off by this plus 2 here in the denominator. So in other words, let's think about 3 to the n over 2 plus 5 to the n and how that compares to 3 to the n over 5 to the n. So here, which one's bigger? Which way should the inequality face? Well, notice the denominator here is bigger. It's bigger by 2. So if we have a bigger denominator, that creates a smaller fraction. So if the numerators are the same, but the denominator is bigger, then that creates a smaller fraction. So in other words, think about it in terms of pizza slices. Would you rather have 1 out of, let's say, 5 to the n pizza slices, or 1 out of 2 plus 5 to the n pizza slices? This is dividing the pizza into more slices, so that's going to give me less. So bigger denominator, smaller fraction. Okay, so this is the direction of the inequality. Now the question is this a helpful direction? So here, let's take a moment to realize that 3 to the n over 5 to the n is 3 over 5 to the n. And so the corresponding series that we're thinking about is the sum of n equals 1 to infinity of 3 over 5 to the n. This is geometric. And the common ratio's absolute value, 3/5, is less than 1. So this is a converging geometric series. Now, does that help us? This was a bigger series that was converging. So here we have bigger and converging, right? BC, bigger and converging. So this does help us. So here we're kind of going to write it out as like a little proof. So we're going to say, note that 3 to the n over 2 plus 5 to the n is less than 3 to the n over 5 to the n. And the sum of n equals 1 to infinity of 3/5 to the n is geometric with the absolute value of r is less than 1, so it converges. Then our conclusion is by the direct comparison test, our infinite series from n equals 1 to infinity of 3 to the n over 2 plus 5 to the n must also converge. So what we're saying is our series is smaller than a convergent series, so it must also converge. Now, before moving on, I just want to give a couple of quick tips because the hardest part for students is really trying to justify this inequality in their mind. So a lot of the struggle has to do with the fact that it's fractions. Here's one technique. What you can do is start by just thinking about how 2 plus 5 to the n compares to 5 to the n. So hopefully you can justify this a little bit better, that 2 plus 5 to the n is definitely greater than 5 to the n. And then from there, if we take the reciprocal of that, so if we have 1 over 2 plus 5 to the n, that would be less than 1 over 5 to the n. So here, we are taking the reciprocal, that's going to change the inequality. And then if I multiply both sides by the same positive quantity, so multiply both sides by 3 to the n, the inequality will stay the same. So hopefully that's another way to help you justify the direction. The other thing I can do is plug in a number to just double check that this inequality holds. So here, if I substitute in, let's say 1, then I'm going to end up with 3 over 2 plus 5, so 3 over 7, and then 3 over 5. So, which would I rather have, 3 out of 7 of something or 3 out of 5 of something? I'd rather have 3 out of 5, right? That's a bigger slice. If there's 7 pieces, I'm getting less. So again, there's a lot of different little ways to think about it, but you really just want to be able to justify to yourself the direction of the inequality holds true. But this type of stuff would all be scratch work to the side, like I'm doing over here, because you do want to state the formal inequality as functions of n. In our next example, does the sum of n equals 2 to infinity of 4 over radical n minus 1 converge or diverge? All right, so this looks really similar to a p-series, except for this minus 1 here. So what we want to do is we want to compare 4 over the square root of n minus 1 to 4 over the square root of n, and think about, again, whether that comparison is going to be helpful or not. So here, which way does the inequality go? Well, this denominator, square root of n minus 1, is the smaller denominator because we're subtracting 1 on this side. So bigger denominator is over here, the square root of n. So if I have a bigger denominator, that's the smaller fraction. So the smaller fraction is 4 over radical n. And now what do we know about the sum of n equals 2 to infinity of 4 over n to the 1/2? Well, this is essentially a p-series, and p is equal to 1/2, which is less than 1. So this is divergent, right? So this diverges. And now the question is this helpful then, right? So the one that we have, this is going to end up being smaller and diverges. So yes, SD, this is the helpful case. So I have something smaller that diverges, then the bigger one must also diverge. This is bigger, so it has no chance of adding to a finite number. If the one's smaller, then it doesn't. So let's make it a little bit more formal. So note that this inequality is true, and this series diverges. So we can say by the DCT, the direct comparison test, the sum from n equals 2 to infinity of 4 over the square root of n minus 1 also diverges. In this example, we want to know, does the sum of n equals 2 to infinity of 1 over the quantity n natural log of n all squared converge or diverge? So here, let's think about 1 over the quantity n natural log of n squared. Well, that's equal to 1 over n squared times the quantity natural log of n squared. So I can distribute the exponent because this is multiplication. And so what do I want to maybe compare this to? So I'm always thinking about either a p-series or geometric. And the p-series that it kind of looks like is 1 over n squared. So let's try to compare it to 1 over n squared and think about which way the inequality should face. So here, uh, they both have 1 in the numerator, but this denominator is going to be bigger. I mean, where we both have n squared on the bottom, but this one, this n squared is being multiplied by natural log of n squared. So this denominator is going to be bigger. So if I have a bigger denominator, that overall is a smaller fraction. So let's see if that helps us. This p-series, the sum of n equals 2 to infinity of 1 over n squared, this is a p-series with p equal to 2, which is greater than 1, so this converges. So basically, does this help? Well, this is bigger and it converges. So yes, bigger and converges is helpful because then that means this one is smaller. And if I'm smaller than a bigger convergent series, then I must also converge. So by the direct comparison test, the original series converges. So yes, we do have to formally show the series that we are comparing it to and how exactly that converges or diverges, and then state that we are using the direct comparison test after showing the direction of the inequality and state our conclusion. Also, just want to point out here that the starting index is 2 because if we had a starting index of 1, natural log of 1 is 0, and we can't start with an undefined term. So the starting index might need to vary just to make sure that the individual terms are real numbers. Now we want to determine whether the series, the sum from n equals 1 to infinity of sine of 1 over the square root of n cubed converges or diverges. So I want to go ahead and point out that the denominator here, the square root of n all cubed, we can think about that as n to the 3 halves. So the square root of n is n to the 1 half, and we would multiply those exponents there. So n to the 3 halves. And so again, what do we typically want to compare to? We want to compare to either a geometric or a p-series. So here, we probably want to compare to a p-series. We see this n to the 3 halves, but what about this trig function, this sine of 1 over n? So here, whenever we have sine or cosine of a function, let's start out with something that we should know back from our trigonometry days. So let's start with noting the fact that sine of 1 over n, that's definitely less than 1. So sine of 1 over n is between -1 and 1. That's the range of the sine function. So sine of 1 over n is definitely less than 1. Okay, well, what we can go ahead and do, if we know this is true, if we divide both sides by the same quantity, the inequality is still going to hold because that quantity is going to be positive here. So basically, we know sine of 1 over n over, let's say, n to the 3 halves, since that's what we're trying to create here, that's less than 1 over n to the 3 halves. So this is true from, our understanding of trigonometry. And then if we have this inequality is true, dividing by the same positive quantity, the inequality will still be true. Now let's see if this is helpful. The sum of 1 over n to the 3 halves is a p-series with p equal to 3 over 2, which is greater than 1. So this converges. And so let's go ahead and take a look here. This is bigger and converges. So yeah, this is going to be a helpful comparison. By the direct comparison test, our original series also converges. Here we want to determine whether the sum of n equals 1 to infinity of arctangent n over n converges or diverges. All right, so let's attempt to use the direct comparison test. We want to probably try to compare it to 1 over n somehow. And so let's start to think though about what we know about arctangent regarding an inequality. So hopefully we remember that arctangent n is always less than pi over 2. So if we think about the graph of arctangent, we know that on the right side, it's bounded above by the horizontal asymptote pi over 2. Okay, so here's already an inequality involving arctangent. We want arctangent divided by n. So if this is true, we can divide both sides by n because n is always going to be positive, and the inequality will still hold. So arctangent n over n is less than pi over 2 times 1 over n. So that's the same as dividing by n, multiplying by 1 over n. And so the question is now, is this helpful? Right? So here, let's think about the sum of 1 over n, because we could just think about pulling that pi over 2 out. Well, the sum of 1 over n is the harmonic series, and we know that the harmonic series diverges. So is this a helpful comparison? We have a bigger series here, and that series diverges. So unfortunately, no, that's not a helpful comparison. If I have something bigger that diverges, this smaller thing, something underneath it, that could still converge. It's smaller. So yeah, it could still converge. So unfortunately, this was not a helpful comparison. And so what that means is that let's try something else. Let's try another comparison. And so here's the comparison that we're going to use. I'm going to write it down and let's talk about where it's coming from. Here's something else that I know about arctangent. Arctangent of 1 is less than arctangent of n for n values greater than 1. Okay, so what's happening there? Arctangent of 1. So let's come over to the graph and kind of think about this for a second. So here, arctangent of 1, if the input is 1, all right, so if the input is 1, all of the remaining outputs of arctangent are bigger than that output there. So what is that output? What is arctangent of 1? If we remember from our trig, it's pi over 4. So the output there is pi over 4. So basically, when I have values greater than 1 over here, all of those outputs are definitely bigger than arctangent of 1, which is pi over 4. So hopefully this inequality does make sense to you. So arctangent 1, pi over 4, is less than all of these outputs over here, right? All of these individual points are bigger as long as we're bigger than 1, right, on this side. So this inequality is true. And then again, what is arctangent 1? It's pi over 4. So pi over 4 is less than arctangent n. Well, now let's go ahead and divide both sides by n. So we have pi over 4 times 1 over n is less than arctangent n over n. So does this inequality help us? Well, let's take a look at this series. Again, it's actually the same one, right? So pi over 4 anyways, times the sum of 1 over n, the harmonic series, once again, diverges. But this time, our inequality is saying that the sum of 1 over n is smaller and diverges. So what we have is now we have a smaller series that diverges, right? SD, this is helpful. So now we can draw a conclusion using the direct comparison test. So I formalize things over here. Note, arctangent 1 is less than arctangent n, which is pi over 4 is less than arctangent n. Divide both sides by n or multiply by 1 over n. We have this inequality, and this series is harmonic and diverges. So by the direct comparison test, our original series must also diverge. A common question is, when should I use the direct comparison test, especially because there's another comparison test? You usually try the direct comparison test when your series is essentially a known series, plus or minus a small fixed thing, like a constant, a bounded trig factor, or an extra term that doesn't change the overall size. So here are a couple of examples. The sum of n equals 1 to infinity of 1 over n squared plus 7. So what we should be drawn to here is the sum of 1 over n squared. That's a known p-series, and it's just off by a constant, 7. So we would ideally want to try the direct comparison test on this one because it's just off by this small fixed constant. And in the second example, the sum of n equals 1 to infinity of 3 over 4 to the n plus 2n, we want to focus on 3 over 4 to the n. 4 to the n is exponential, so it's going to dominate 2n. So 2n is an extra term. It's not a constant, but it's not going to change the overall size. We want to focus on that 4 to the n in the denominator. And 3 over 4 to the n is geometric, so we could use a direct comparison test here, or try a direct comparison test because it fits that mold of basically looking geometric and it's only off by a term that doesn't change the overall size. And then finally, the sum of n equals 1 to infinity of sine n over the square root of n cubed. So what we're thinking about here is 1 over the square root of n cubed, or 1 over n to the 3/2, which is a p-series. And even though sine n is involved, that's a bounded trig factor. We know that the sine function is bounded above by 1, so we can think to try the direct comparison test. So if the terms only differ by something that is clearly smaller or larger, depending on the comparison you're trying to shoot for, or a bounded factor, we can try direct comparison. In practice, use direct comparison if you can trap it using inequalities. And one last thing, we should only use direct comparison tests on series with positive terms.